So if you wanted to add that to there, you could. Friday, okay, chapter 3 assignment due. Okay. All right. So we last left off talking about eclipses. And remember, for eclipses, I went ahead and I made this the sun. Wait, no, I made this the earth. And the sun was over there. Okay. And then I was the moon. And we kind of talked about how you could get 2 types of eclipses. These actually are videos that I made. So hopefully the internet's working for us. I have a friend at the observatory in the astronomy club, and he's like, watching a lunar eclipse unfold is kind of like watching paint dry. So I don't know. So you're going to see when this finally comes up that actually I tried to take excerpts of the lunar eclipse. It was a total lunar eclipse. What's that?
Fast forward.
Yeah, fast forward. Come on. Oh, here it comes. It's there. There is a delay. Or maybe I think I'm going to have to get out of here to do it. It's Monday. It feels like Monday. Oh my gosh. All right. So this is one I made last spring. And you can see there's 27 minutes. I'm not going to show you the full 27 minutes. But actually it's going on right now. Very, very subtle. We talked about a terminator, and for a normal moon, a terminator is the thing that separates the light side from the dark side. Okay, this does not look like your typical terminator. That actually is the Earth's shadow, and the moon is passing into the Earth's shadow. The moon looks kind of creepy flat, okay, during an eclipse. So fast forward, you can see these down here. So then go up to here. Not a whole lot of change. And then I must have gotten some pictures here. So I'm using my DSLR camera, and you have to adjust the light coming into it. So it's kind of dark right there. But that is a lunar eclipse. And it kind of jumped from, you saw a big change when I had. The other thing is I did get 5 seconds worth of solar eclipse then, this fall. Let's see. So the solar eclipses happen when the moon is over here in its new phase. So basically the moon's disk covers up the sun's disk, and we get a solar eclipse. Blink and you'll miss it. Now, I didn't get the whole solar eclipse because I was fighting clouds, so I just got a little bit of it. Okay. See? Did you blink? Did you miss it? All right. So there actually is kind of the eclipse underway. This is a humongous sunspot that observers during this particular eclipse were so excited about. If you are ever where an eclipse is going on, a solar eclipse, and you want to see it, I do think it's safe to take like the welder's goggles and hold it up to the sun, but never look at the sun or fry your eyes. Okay. So this particular telescope has kind of like a like a mylar type of sunglass material over the end of it. So it safely filters out much of the solar radiation before it comes back to the eyepiece. So there it is. There's the moon's shadow, or the moon passing in front of the sun. So then the last topic we need to talk about here, it's Monday, is this idea of how do planets move? How do planets move? Well, one of the things is we know that the other planets orbit the sun, right? So if I'm changing this from the Earth to the sun. If this is the sun, okay, the Earth orbits the sun, okay, and all the other planets orbit the sun. So as they orbit the sun, actually, when we look at them, whether they're an outer planet to us or an inner planet to us, you know, we have Mercury, Venus, Earth, Mars, you know, Jupiter, Saturn, Uranus, Neptune. We're going to see them kind of reposition themselves against the background stars. Now, they are all going counterclockwise, just like we are. Counterclockwise, okay? So all the planets are going counterclockwise, but they're going at different rates. And one of the things we're going to talk about soon in Chapter 3 is that the inner planets are going faster than the outer planets. The outer planets are kind of dogging it. The inner planets are zipping around faster. So what we usually see is basically two things. We see the planets move against what we call the ecliptic. Okay. Now, as I'm taking my hands and going like this, this is the plane of the ecliptic, right? Because it holds the Earth orbit and the sun. Okay. And it's like one big frisbee for the other planets too. They all orbit on the ecliptic plane, the plane of the ecliptic. So when we look at them, they actually, a lot of times maps will show you the ecliptic, okay? And the ecliptic is where the sun goes, okay, across the sky through the course of the day. And it's also, the ecliptic is where you're going to see those planets. So they're kind of in a line. Usually planets will move what we say eastward. So let me see. We decided this is west, okay, this is east, okay. Mostly planets go deep, 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 deep. Now, they do that like from night after night. I should say against the background stars. Now, your background stars are also moving a little bit night after night. They rise 4 minutes earlier each night. But usually planets will go eastward, okay? And actually that made sense, okay, if you go ahead and put, I know it sounds weird, but put the Earth in the center of everything, put the sun orbiting the Earth, put the moon, which it is orbiting the Earth, but put the stars orbiting the Earth, put the planets orbiting the Earth, and you're like, oh, I can buy that, okay? The planets are orbiting the Earth. I know it's strange. But that's called the geocentric model, okay? But what didn't make sense was every once in a while they would go what we call retrograde, okay? Retrograde means it goes a little bit backwards. The planet goes backwards against the background stars. And it's called retrograde motion. And they couldn't explain that. Okay, so direct motion can be explained if the planets orbit the Earth, which I know is strange. It's not the real deal. Okay. But retrograde motion cannot be explained. So here we have Mars from June to November, okay, against the background stars. Mars against background stars. Okay. So I said that the eastward motion against the background stars is normal direct motion. So here we see Mars doing the normal thing. So this is direct. So it's going normal, 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 normal. Okay, right about July 30th or so, it changes to indirect, retrograde. Okay, and then it will go back about September 29th to direct motion. Okay, so those little loop-de-loos, those little stop, go backwards, and then go forward again, could not be explained with putting the Earth at the center of their motion. But if we change from the Earth at the center of the motion, which we all kind of scratch our head, and we put the sun back in the center of the motion, things actually fall into place. Putting the sun back into the center of how the planets orbit is called a heliocentric or sun-centered model. Okay, I'll show you why that is. And this is kind of hard to describe sometimes, but aside from this, have you ever been like passing somebody in the left-hand lane? I know you have. Okay, there's somebody going slower in the right-hand lane. Okay, but you're both going in the same direction. As you know, they're way up there. Okay, you're passing them, getting ready to pass, and you're gaining on them, right? And you kind of see them still moving this way against the background. The background could be trees, whatever's out there in that part of the road. Okay, so they seem like they're moving, you know. Now, as you go right next to them, close to right next to them, they kind of just for a moment, it's almost like they feel like they're going backwards. Okay, and then you go past them, and then they go forward again because they're back there and you're against the background. If you've ever felt that sort of feeling, that is actually what happens with the planets. Okay, I'll show you. Well, just kind of showing you walking here. So the blue, the gal in the blue actually could be the Earth, and I'll go ahead and show the other one. The gal in the blue is the Earth. The gal with the red shirt, or person with the red shirt, is Mars. So Earth and Mars, Earth and Mars. Earth is closer to the sun. Earth goes faster in its orbit than Mars. Mars is dogging it just a little bit. Okay, so it happens that the Earth is going to lap Mars. So here we have, let's go ahead and let's go over to the planet themselves. Here we have Earth, okay, going to approach Mars, okay, and then it's going to actually overcome Mars. So here we have positions 1 through 7, and 1 through 7, where Mars looks against the background stars is written up here. So actually, the way this works is we would see Mars go direct motion. Oops. We would see it go direct motion, okay. Here it's retrograde. Positions 3, 4, and 5. Positions 3, 4, and 5. When we're passing Mars, it appears to go backwards. Okay, and then kind of 5 and 6, okay, it's back to direct motion. So this idea of going ahead, and this was a big hairy deal of now not putting the Earth in the center of everything, but putting the sun in the center of motion. If we put the sun in the center of motion, we can make sense of that backward motion of Mars against the background stars. Okay. So the last figure then says, well, why not go with the sun in the middle? Why not go with the sun's in the center and the planets orbit the sun? This actually was one hang-up from the sun-centered model. This thing called parallax, and this is kind of our first look at parallax. But we'll be talking more about it. This right here, okay, I was doing this on my way to work today. Yeah. So what it says is you can look at what parallax is by just, if you hold your finger in front of your nose, okay, and look at a distant object. Everybody do it. I'll do it this way. Okay. Look at kind of a distant object and close one eye and then close the other eye and look where your finger goes. Does it like move? Yeah, that's parallax. What it is with your different eyes, that's kind of like you're here with your right eye and then you're over here with your left eye. Okay, and it like moves against the background. Now take your finger and put it as far as you can and do the same thing. Does it move less? Yeah. So the thing with parallax actually is the farther you locate your object of interest, kind of your nearby object, the farther your nearby object is, the less parallax you see. The closer it is, the more parallax you see. So along those lines, what people said is, oh my gosh, if the Earth is orbiting the sun, okay, if the Earth is like here in January, and if the Earth is over here in July, or did I mix that up? This we decided was January, okay. If it's over here in December, okay, and if it's over here in June, 6 months apart, then actually when we go to look at those stars that are different distances away, those stars are going to kind of scramble, change their positions, because we are changing our position because of parallax. Parallax will make them look different. They make different patterns. Okay? And actually, this little figure here shows you, and we do see parallax in kind of relatively nearby stars. They couldn't find any back then, per se, but so if we take a star, this is our nearby star, okay, in July, okay, actually our nearby star will look like it's here, okay, like here, against those other stars. In 6 months later, in January, that star will look like it's over here, much the same as your finger, kind of looks different when you open different eyes. Okay, so the fact that they couldn't, on a routine basis, 6 months apart, see parallax in the stars was like a kind of a non-starter. They're like, hey, we cannot be relocating our position around the sun. Okay? But we're going to say Galileo kind of had something to say about that. All right. It's like my computer is possessed. There it comes. So this reminds me of the movie Gravity with the, Sandra Bullock's just out there. Scary stuff. Yeah. I thought it was a little long. I thought it was good.
It's a little long. I think it's a certain movie. You have to be interested in that topic to kind of like that movie, I think.
Maybe so. One of the things we're going to talk about after unit exam is gravity. We'll talk more about gravity then. But I kind of want to kind of think historically. This kind of puts things into perspective historically. And you may or may not know that when it comes to science, math and science, actually the Middle East has kind of been a storehouse for knowledge. Kind of built on it, and that sort of thing. But when it comes time to astronomy, historically, ancient people, that was probably their entertainment. You know, they told stories about the pictures in the sky. And astronomy actually was helpful when it came to time to plant the crops and interpret things in the sky. Okay, so much of our mathematical and scientific heritage came from the Middle East. Road trip. But this great library of Alexandria, it got like tumbled down. I can't remember who came in and created it, but it happened recently too, didn't it? I mean, not Alexandria, but something else. So astronomy, a long time ago. The way the crescent moon is, kind of whether it's kind of nice and full or kind of tipped, actually goes with seasons. So you could know when your rainy season was going to come. This is a really old monument, these stones, Stonehenge, that actually have sweet time, like during the solstices and the equinoxes. These things cast shadows in a cool way. But that was back 2750 BC. That's like a long time ago. This one right here, you've heard of sundials. This kind of reminds me of sundial. On my list of things to do, just recently look into, don't you think we should take like this flagpole and turn it into a big sundial? Yeah, I'm thinking. You'd help? It's there, you know, but we can't vandalize, so we'll have to look at it, do it. But the sundial actually can help you know what time of day it is. This one, the unit exam review sheet that I gave you, actually, this is one of the interesting things I went ahead and pulled out, and it's on your exam for Friday. This is actually the sun dagger, and only on noon on the summer solstice does that light, that knife, line up with right through the center. So that's on your unit exam. We have total civilizations that were kind of built around what was happening in the sky. This is a way to navigate using the stars in the sky. It's pretty cool. Okay, so, 500 BC, the Greeks were going strong. They didn't really, the scientific method came after that, but they actually made some inroads with regard to things that you just automatically think of when you think of science. So, like, for instance, they said that we should rely only on natural explanations, not supernatural explanations. So that kind of takes the whole God's thing out of the picture, right? They said, where possible, use numbers, use mathematics to kind of think through your ideas. And they said that when you're developing your idea, and actually in the scientific method, we still definitely rely heavily on observations. You know, you're like, duh, right? But take all of your observations, and don't just take the ones you want. Take all of your observations, and they have to be the way you think it's working needs to be consistent with your observations. All right. The other thing that they did was they developed the idea of scientific model, like the celestial sphere is a scientific model, to kind of describe their observations and their thoughts about things. So this actually also made it to the test, this little thing down here. So back in 240 BC, what they did was estimate the the circumference, sorry. They estimated their circumference, it was the radius. Estimated the radius of the Earth. Final answer. Okay. So the way they did it was at the same time, okay, they knew the distance between two locations. Okay, so the distance was known. And so they went where the sun was at zenith at one location and saw what angle the sun made at the other location. It was 7 degrees. Then actually they could take that 7 degrees and go back to the center of the Earth and estimate the radius of the Earth. Okay, you don't need to know how to do it yourselves, but that's kind of in a nutshell what they did. Does it say radius? Well, no, I said radius, but it is circumference. Darn it. Okay, so the angle was 7 degrees, and actually that's a whole circle is 360 degrees, so 7 over 360. They used that as that distance, and then came back to anyway. Okay. So in terms of understanding cosmology, understanding the universe is the fabric of space and time, all the matter and energy in our universe. So at the time that the Greeks were kicking it around, they could see 5 planets. They could see the 2 inner ones. They could see Venus, or they could see Mercury and Venus. And then they could also see Mars and Jupiter and Saturn. Okay, but they couldn't see Uranus and Neptune. Okay, and we already kind of talked a little bit about these bullets here. That except for the whole retrograde motion of planets, the direct motion of planets could actually be explained if you put the Earth at the center of them moving. We actually call that a geocentric model. Okay, so geocentric model makes you giggle, okay, but that's putting the Earth in the center of the planets moving and the sun moving, orbiting the Earth. So notice we're going to come up with something called the Copernicus revolution, but who finally said, it's the sun that actually the planets orbit the sun. But clear back in 2060 BC, Aristarchus said the same thing. So the Ptolemy, the P is silent, the Ptolemaic model, or Ptolemy, he was still with the whole Earth in the center of the planets orbiting the Earth. So he was kind of the last hurrah of, I think, the geocentric model of the way our solar system is. He finally explained the whole little backward motion of the planets with putting the Earth at the center by introducing something called epicycles. So these right here are epicycles. Those were places where as a planet orbited the Earth, the planet would do kind of a little loop-de-loo around an epicycle. And in doing the loop-de-loo, it would go backwards, and then it would go on direct motion, then retrograde, direct motion, retrograde. So this violates the keep it simple, stupid model. Actually, we're going to come up with one of the, if you know you're on the wrong track if you make it too complicated. So this actually is not part of the keep it simple. He's violating that. So again, the Middle East was a cradle for keeping the knowledge during the Dark Ages. So one thing about science is that we definitely build on what others know. You know, I can't imagine starting from scratch. So there's Copernicus. And like Aristarchus, he said that, nope, the sun is, the planets orbit the sun. Okay. So there are 4 names coming up, and he is the first of 4 names to know. And he was encouraged to go ahead and publish his helio or sun-centered model. And he was a little shy about the whole thing because he thought he was going to end up with like what Galileo ended up with. So Copernicus, the problem was, and I'll go ahead and circle on this slide, the problem was that both Copernicus and then his student Tycho Brahe were stuck on the planets, on the shape of the orbit of the planets. They were stuck on the whole idea that the sun was in the center and these were circular orbits. Yes.
Or the date's wrong because he would have been dead when he was born.
I'll have to look into that.
Higher than.
So he would have been 70, he's 70.
How old would he have been? 73 if he lived.
Yeah. I'll look into that. Is this, he's saying, this does not make sense.
No.
If he hired him.
He could just be like taking over his thoughts and ideas too.
He could have, yeah, he could have. But I do think that there was, it sounds like, the way it reads is they were, yeah.
Actual students, yeah.
Thanks, we'll look into that. But assuming then, I do think that Copernicus was near the end of his life when they made that connection and passed the baton from Copernicus to Tycho Brahe. But it couldn't have been dead. All right. So the thing about Tycho Brahe was, now he didn't use a telescope, but he had a fancy place to make some great measurements of the stars and the planet's motions. So what you see over here in the lower right-hand corner, okay, that's some of Tycho Brahe's toys. So Tycho Brahe was still, working on the sun-centered model of our solar system. And while he was doing that, actually, he did observe a supernova, and he called it just simply a nova. But a supernova is different than a nova. A supernova is when a star blows up. Either it's a white dwarf star or a massive star at the end of its life, supernova. So he did see that, and actually the fact that it went from just blank or one tiny little star to that, okay, that means that was an indication that the heavens could change. So that was in the right direction to kind of cutting loose of kind of supernatural, the heavens must be perfect. He also saw comets. Okay. But he still could not, again with circular orbits of planets, he still could not fully predict where the planets would be. He could not he could explain retrograde motion, but he could not accurately predict where the planets could be. One of the things about the scientific method is when you come up with ultimately your hypothesis, which can be elevated to a theory, you have to be able to predict things from your hypothesis or your theories, and he still couldn't. So he hired, let's see if our dates work out, he hired the third of 4 guys. He hired Johann Kepler. So Kepler didn't do the measurements, but he used Tycho Brahe's measurements. Okay, so there's Kepler. I think these men were kind of haunted by trying to solidify the sun-centered model. Does 1571 work? I guess.
Yeah.
Okay, good. So the breakthrough came when Kepler, like I kind of alluded to, when he broke out of the mold that the orbits needed to be a circular shape, and instead made them oval or elliptical. Okay, and then things fell into place for Kepler based upon Tycho Brahe's observations. So Kepler came up with 3 laws. These laws are just limited to how the planets orbit the sun. Kepler's 3 laws of motion of planets about the sun. And we're going to talk about them individually, but they're kind of summarized here. The first one is the shape of the orbits. I already told you it's an oval or an ellipse. The second, Kepler's second law is that planets move faster in their orbits when they are closer to the sun. Now, the way this works is actually, remember we talked about perihelion and aphelion? Okay, perihelion is when the Earth is close to the sun, and aphelion is when the Earth is far from the sun. So the Earth goes faster at perihelion and slower at aphelion, and all the planets do. His third law was the one I mentioned about the fact that we get to go faster than Mars in our orbit. Okay, the closer the planet is, the faster it moves in its orbit. Planets with orbits further from the sun orbit the sun at slower speeds. So this is his first law. And it says the shape of the shape of the orbits of the planets. So that's a circle. Now, to make a circle, you'd put in the center of the circle, you could attach a string and then attach the other end of the string to a pencil and draw around. That's a circle. So for ellipses, what you need to do is have the same length of string, but you need to have 2 nails, and it's kind of like a spirograph, right? Where those 2 nails would be what we call the foci, and you draw a circle around like that. Okay, that is an ellipse. Looks like an oval, doesn't it? But ellipses have 2 sweet spots called foci. And actually a circle is an ellipse, but the foci overlap. They're in the same position, same place, 2 foci. So one of the things with ellipses is we talk about their eccentricity. Eccentricity just means kind of how flattened out they are. So the eccentricity can go from not flat at all, eccentricity value of 0, all the way, actually I think it's an eccentricity value of 1. Okay, so they're getting more and more eccentric as they're over here. This is increasing eccentricity. Another thing about ellipses is that they're kind of, their ovals tend to have a long part, okay, and we call that the major axis. And then they have the short part, and we call that the minor axis. We have semi-major axes is basically take the major axis and you divide it in two. That's a semi-major axis. The semi-minor axis, you take it the whole minor axis and divide it in two. Yeah. So that was Kepler's, or this is Kepler's first law now with all of that in mind. So Kepler's first law said, hey, it's not a circular shape. Our orbits are not, it's a circular shape. Our orbits are in an ellipse. Specifically, the sun is at one foci of the ellipse, the elliptical orbits of all the planets. So, let's see, how do I do this? If that is the Earth, remember we said that the Earth has a perihelion when it's closest. We said the Earth is at aphelion when it's farthest away. And what Kepler said, yeah. So what I was going to say is that if we look at where Mars would be then in this, I don't know if it's going to fit, Mars would have a similar orbit in the plane of the ecliptic, and it would be with the sun at the same foci as its ellipse. Kepler's second law goes like this, that basically, I know it talks about equal areas and equal times, but it said at perihelion it's moving fastest. And actually this is consistent with Newton's general laws of motion. At aphelion it's moving slowest. The thing about equal areas in equal times goes like this. If it's moving fast over here, it goes, I'll call that location A, location B. It goes like really fast, right? The area it talks about is to go back to the sun. This is the area. If for the same time period, if now we turn our attention to aphelion and it's just going slow, it's going d d d d d d d d d d in the same time period. So we could call this C and D. That's all the farther it's going to get for the same time period. We can then take this area and bring it back to the sun, and these two areas are the same as long as the time period is the same to go from A to B and C to D. That's all it means. But the consequence is it moves fastest at perihelion and slowest at aphelion. His third law was the fact that the closer the planet is to the sun, the faster it will move in its orbit. And again, this actually too is consistent with Newton's general laws. So I know it's like, well, what's the p squared? What's the a squared? Well, the p squared is period. So that's the orbital period. That's what the P stands for. So for I know Pluto's not a planet, right? Okay. But for the planets here, we have period in years of how long it takes to complete one orbit about the sun. Notice that it takes almost 250 years for Pluto to make one orbit about the sun. I know. So if you square this, okay, raise it to the second power, that's related to its, A is the semi-major axis. Okay, remember we have a major axis and a minor axis for ellipses. Take half of the major axis, and that's the semi-major axis. If you raise this to the third power, they are approximately equal. So to test this, you would see, are these equal? You know, in some cases, they're closer than others. That one's really out. Saturn? Oh, I see. Duh. You know what I'm doing wrong? I need to go over here. Yep. See if these are equal. I'm like, dang, that's terrible. That's not a correlation. Okay, these are. This is where that first column is squared and the second column is cubed. Clear as mud. Well, let's just go ahead and stop there for today. We don't have a lot of slides left, okay? But that'll give us something to talk about on Wednesday. Yeah, and get out there and see that funky moon. It's supposed to be clear and hot.